Hello everyone. So now that we know how to define angular position with our new unit that isn't really a unit, radian, right? 1 radian being when the arc length and the radius are exactly the same, 2 pi radians in a full circle. Now we can start talking about motion of things that are rotating, okay? And so we're going to start out here with a little device that normally I would show you in the lab, but since this is a movie, I can't, right? But you'll see it in lab. It's this bar, right? Little aluminum bar, painted black, with these brass masses at the ends of it, okay? And it's mounted to this thing, which is a rotary motion sensor. A rotary motion sensor measures rotations. Right? It is to our rotation unit what a motion detector or the encoder wheel on the bottom of our fancy carts are. Right? It's going to be how we're going to measure rotations experimentally. Okay? And it's one of the nice things about it is it's very, very low, almost no friction. Okay? So, since I can't show it to you live, right, I just have this kind of picture of it. Okay? So imagine we got it spinning. Like that. What do you notice about that motion? Let's watch it again. What do you notice about that motion? Well, it's one way around. And does it look kind of constant to you? One more time. Looks like a pretty much constantly rotating. Well, if we made a graph of angular position versus time in radians and seconds, what do you think that would look like? Now, hopefully you're saying to yourself, well, this looks a lot like maybe what the toy car did last year, constant velocity, right? But rotating. In which case, the graph would probably look like this, right? A linear graph, right? To show that it's constantly rotating. If you are not comparing rotation and linear analogies constantly during this unit, you are doing yourself no favor. Okay, we have spent a ton of time developing a lot of models for linear motion and things. Okay, in here now we're going to take them and tweak them and make them rotate, but they are all related to the linear analogy, right? So kind of keep that in mind, right? Since this is linear and goes through 0, 0, we can say that in this case the angular position and the time would be proportional to one another. If I let it spin for twice as long, it would rotate through twice the angle in radians, of course. So y equals mx plus b, our y variable is theta, the angular position. And that equals the slope, which I'm just going to put a number symbol here. I don't know how fast that was going, right? Units, rise over run, radians, seconds. So what would that mean? Let's make a for every statement for that. So it means for every second, every 1 second, the angular position increases by this many radians. It's telling you how many radians it's rotating through every second. Does this sound like something we've seen before, but linearly? How many meters something goes every second? Now it's how many radians it rotates through every second. Well, we'll give this a name in a minute. What's the x variable? Well, it's time. And the y-intercept is essentially 0 in this basic case, right, where we start from rest, if you will. Or sorry, where we start from 0 position. So what do you think we're going to call that slope? Right? If how many meters we go every second is the velocity, then this is going to be the angular velocity. It is denoted by a lowercase omega. This is not a W. Okay, it's got rounded bottoms. Okay, it's rounded on the bottom. Okay, it's an omega. If you need to look it up to see it bigger, go ahead and do that. Lowercase omega. So we're going to define angular velocity as the slope of a graph of angular position versus time. Okay, it's a slope of an angular position time graph. Kind of like linear velocity is the slope of a position versus time graph. We'll see the analogy. If we pick 2 points, rise over run is the slope. The rise is how much the position changes. The run is how much the time changes. So if the angular velocity is the slope, right, then the angular velocity is rise over run. Right? Angular position over time, or if you will, the rate of change of angular position. And yes, we can eventually, when we want a more complex motion, turn that into a derivative, but that's a ways away. Okay? So this is really our basic definition, right? It's the slope of a graph of angular position versus time turned into symbols. Now, delta x, right, the change in linear position, had a special name. It's called displacement. So delta theta, which is the angular position, right, the change in the angular position, also has a special name. It's called the angular displacement. And just like any change in, you find it by taking the final minus the initial value. Notice how, just like we did in motion, nothing means final, and O means initial. Okay? O for original, or 0, if you will. Now, this is a little harder to visualize than linear. So I made this little thing. It's one of the things I'm probably most proud of making in a PowerPoint. So I want you to watch the angular displacement of this thing as it rotates. Ready? So there's the initial angular position that it's starting at. There's the final angular position, again from 0 all the way around, right? That angle. And this is the angular displacement from initial to final. Watch it again. Right, so there's the angular displacement. How far the angle it rotated through in radians, right? You could do this in degrees or revolutions, but radians is what we're using a lot in here. You with me there? One more time because I like it. There you go. Okay. Now, one thing I want you to notice here. Did you notice that all parts of the object rotate together? Because this is what we call a rigid object rotating about a fixed axis. You'll hear that phrase a lot. Okay? Rigid object rotating about a fixed axis. And because it's a rigid object and it's rotating about a fixed axis, all parts of it rotate through the same angle in the same amount of time, which means it has the same angular position, the same angular displacement, and the same angular velocity. All parts of it. We take a point here, right? It's rotating through the same angular displacement in the same time. Point out here, same thing. Now, one little thing we can do here, well, a couple little things. First off, if it doesn't start at 0, right, 0 angular position, well, just like, again, think of the linear analogy, all that's going to do is, it's not going to change how fast it rotates, right? It's just going to change where it starts from, which would be the y-intercept. So the y-intercept of an angular position versus time graph is what's known as the initial angular position, theta sub O. So if we want to make a math model of this slightly more complex version, y equals mx plus b, y variable is the angular position, that equals the slope, which we have now defined as the angular velocity, x variable is the time, plus the y-intercept, which we now know is the initial position. And because it's addition, we can flip this, right? It's commutative. Oh, I'm sorry, this is for constant angular velocity. How do I know it's constant? Because the slope is constant, and the slope is the angular velocity. Right? Linear graph. Again, if you think about it, this is exactly like the equation we developed for linear constant velocity. Same equation, just rotational. Now, here's one I wish I could show you, but you're just going to have to buy this. What if we rotated it clockwise? You remember before it went around counterclockwise? And I hope you know which clockwise and counterclockwise is. If not, we'll have to talk about that, right? If you don't know analog clocks anymore. Well, what do you think it's going to make the graph look like? So this is analogous to if an object is going to the right, and then what if it's not going to the right, it's going to the left. Okay, what does that do? Well, that changes the direction of the velocity, which changes the sign of the slope. So this graph would look like this. Linear, goes through 0, 0, but now it has a negative slope. Angular velocity is in fact a vector. Now, rotational vectors are a little weird, okay? They're a little different than linear ones. But in this case, there's really only two angular velocity directions, all right, to it. It can either rotate counterclockwise or clockwise. And the traditional rule of thumb is that counterclockwise is positive and clockwise is negative. Counterclockwise is positive, clockwise is negative. Okay? I believe that's because of the way we do angles. If you think about like doing degrees, right? You get a bigger angle as you go counterclockwise around. Right? So that's the positive direction. So it really doesn't matter, but you got to define one way as positive and one is negative. So this is the way we typically use. Now, here's something that'll blow your mind, all right? If you want to try to remember this, besides just remembering counterclockwise, positive, clockwise rotation, you can use something called the right-hand rule. If you do enough physics, there's all these right-hand and left-hand rules for different quantities that help you, because of vectors, sometimes all the way into 3 dimensions, figure out the directions of things. So, if you take your right hand, and you better use your right hand or you'll be backwards, and you curl the fingers of your right hand in the direction of rotation, the vector is in the direction of your outstretched thumb. Outstretched thumb. So stretch your thumb out. Rotate your fingers in the direction of rotation. So if you go counterclockwise, what direction is your thumb point? Your thumb points out. Right? Out is positive z. Right? If you rotate clockwise, your thumb points in. In is always negative in a typical right-handed 3-dimensional coordinate system. So it conforms to that. You with me? Counterclockwise, your thumb points out. Clockwise, your thumb points in. The right-hand rule. Now this is why rotational vectors are a little weird. They don't point in a direction. You can't like draw an arrow in a circle, because that would kind of be weird. Like, what direction is it pointing? Right? So instead, you rotate around the vector. The vector is in the direction of your outstretched thumb. It's either out or in, right? And you rotate around it. Strange little things. And by the way, you notice how I haven't been putting arrows on these? I don't know why that is, but it's traditional in rotational quantities not to put an arrow above it, even though they're vectors. Go figure. Like, I don't know why. When I first started teaching, I used to put arrows on everything. But then when I started teaching AP, I realized they didn't, and I didn't want to, confuse people, so I just started leaving them off. But they are vectors. Maybe it's because they're different kind of vectors. I don't know. So something that is spinning, right? A point on that object not only is rotating, but it's also moving. It also has a linear velocity, right? Not only does it rotate through an angle in radians or degrees or revolutions, but it also moves a distance, doesn't it? Pick that point on the outside, right? It moves in a circle. Since it's moving constantly, we can describe the linear speed of it and the rotational speed of it and kind of compare them to one another. So, if it's moving for an entire trip around, like we just saw, what distance does it cover? Well, it goes in a full circle. The distance around a full circle, right, is the circumference. And the time to go around once is called the period. Circumference is 2 pi r. Period is capital T. Right? You might remember that from circular motion. Right? Capital T for period. Lowercase t is just generic time. Period is the time to go around once, time to complete one motion. And then, because this is multiplication and division, I can regroup these and reorder them if I want. So I'm going to draw it like this, and there's a reason why, you'll see in a moment. So we can write the linear velocity as 2 pi over the period times the radius. Now, let's check out the angular velocity, which when it's constant we defined as the angular displacement over time. Well, for one time around, what's the angular displacement? What angle does it rotate through one time around, as we found, right, in our angular position post lab? That is 2 pi radians. And the time to go around once is still the period. So we can also find an angular velocity by taking 2 pi divided by the period. fact, in a lab, that's often the way we would do it, right? Period's often a fairly straightforward things to measure. How long does it take to go around once unless it's going really fast, right? And so you just take 2 pi and divide that, and you've got the angular velocity. But look, 2 pi over the period is right there as well. So if we substitute, we can relate the linear speed of a point on a rotating, rigid object rotating about a fixed axis to the angular velocity of the entire rigid object rotating about a fixed axis. Because remember, a rigid object rotating about a fixed axis, all points have the same angular velocity. But if you notice, points at different radii are going to have different linear speeds. And notice they're proportional. If you double the radius, that point is going twice as fast linearly. Why? Well, isn't it traveling in twice as big of a circle with twice the radius? So twice the distance in the same amount of time. Now this is radian measure, and that fact might help you remember. Remember when I first learned this, I often sometimes would forget, is it V equals omega r or omega equals VR? Well, work the units. It's got to be this, right? Because angular velocity would be in radians per second, right? Radians per second. And radius would be in meters. And a radian per second times a meter is a meter per second. Remember, a radian is a name, not a real unit. And therefore, right, speed would have units of meters per second. So that works. If you flip these around, if you thought it was V equals omega r, or sorry, omega equals VR, right, V times R, you'd have a meter per second times a meter, which is a meter squared per second, which is a whole lot of nothing. Right? So it's got to be in radian measure here. You can't put degrees in and have this work out, right? And it's got to be in this order. Okay. So we now have 2 ways, right, to change linear quantities into rotational quantities. S equals theta r. S is the distance it moves as it's rotating, right? The arc length. Right? Theta is the angle it's rotating through. V is its linear speed. And omega is its angular velocity. With me so far? Okay, let's keep going. Now, we don't only need to know about rigid objects rotating about fixed axes. We also need to know about rolling objects. And 99 times out of 100, we're going to have, when we talk about rolling objects, we're going to talk about perfect rolling, which is rolling without slipping. There's no slipping on the contact point between the bottom of the rolling object and the floor or the table or whatever it's rolling on. Okay? This makes it much easier to describe. And we're going to talk about different aspects of this as we go throughout this unit. But consider a disk rolling without slipping at constant velocity. Now, if you notice here, the outside point is not moving in anything that we would recognize as constant velocity, right? It's not moving linearly. It's rotating and moving linearly. It's moving from left to right, and it's moving, around. But there is a single point which is moving linearly. You see that point at a constant velocity? What is that point? That's the center of mass, right? So while most points rotate and move linearly, the center of mass moves linearly at a constant velocity, which we call VCM. So the CM stands for center of mass. So this is the velocity of the center of mass. Oftentimes we describe the motion of a perfectly rolling object, rolling without slipping, by using the center of mass velocity, because that's kind of easier to wrap your brain around what it's doing, right? Rather than this weird loop-to-loop pattern here. Okay? Now, here's some fancy diagrams, okay? So here we have an object, a thing, maybe a disk or something, which is going to roll with constant velocity, perfect rolling without slipping. Here's the center of mass. The center of mass is going to have a speed, a constant speed, which we are going to call VCM. And I want to know, if we look at this point at the bottom, as this thing rolls, how far does this point move? You with me? So this red line here is how far the center of mass is going to move. Right, it's going to move that far. How far does this point move? Did you see that? Watch that again. Center of mass moved this far. How far did the point on the outside move? Well, let me show you another way of looking at it. Okay. Do you notice here? This is how far the center of mass moved, which is exactly the same as the bottom moved. This is true only if you're rolling without slipping. Right? It's got to be rolling without slipping. And what did you notice about this distance? One more time, people. They're all the same distance. They're all the same distance. So, if we drop a little vertical there, right? That's the angle it rotated through, theta, the angular position, right, in radians. That's the arc length, a point on the outside moved, but that is also the distance the center of mass moved, only if it's rolling without slipping. Right? If it's slipping at the edge, they'll move different distances. Right? So rolling without slipping, those two things have to be the same. And of course, we know how to relate the arc length to the angular position and the radius. We did that, lab. So really, this S here means arc length, but it also means this is the distance the center of mass moves. Now, it's not traditional to call this SCM. I don't know why, right? Because that would be helpful, because we have V and VCM, but oh well. So this is, it's the arc length, but it's also the distance the center of mass moved. So we can relate the distance the center of mass moves to the angle it rotates through and the radius. Isn't that fancy? Perfect rolling without slipping. And if we take and divide both sides by the time, why not? Notice what we have over here. We have distance over time. This is the distance the center of mass moved, divided by the time. It's moving constantly, so what is that? That's the speed of the center of mass. And what's angular position over time? That's the position it rotated through in the time. Yeah, that's the angular velocity. So, we can relate the speed of the center of mass to the angular velocity. Now, I know this looks like the equation we just derived before, right? But it isn't. This is VCM, right? When we had V equals omega r before, that was a speed of a point on the outside of the rotating object. Rigid object rotating about a fixed axis. This is the speed of the center of mass, right? How fast it was moving to the right as it rolled. But that can be related to the angular velocity in the radius. And again, these need to be in radian measure for everything to work out, unit-wise, so if you forget the order. So these two equations can describe a point on the outside of a rigid object rotating on a fixed axis, but they can also describe the distance and the speed of the center of mass for a perfectly rolling object, which means rolling without slipping. Sometimes they call this perfect rolling or the rolling condition. Right? If an object meets the rolling condition, it's rolling without slipping, and then these things are true. That was a lot. Right? So that's a lot about constant velocity rotating and constant velocity rolling. Right? And you remember we did a whole unit of this linearly. It took us several weeks. Toy Car Lab started it out. We built a whole lot of ideas instead of doing it in like a half an hour in rotation and making everything harder. Rotation.